Welcome back. So in today's lecture, what we are going to do, we have already done the basics of the microstrip antenna. So we'll just try to brush up through those basics related to the fundamental mode. Our main stress of today's topic will be analyzing the higher order modes of the regular shape geometries, which we have done already. That is a rectangular patch, circular patch and equilateral triangular geometry. So that's why I have given the topic name as the understanding of the designs of microstrip antenna. Why understanding? Because remember, when the microstrip patch dimensions are fixed, then with respect to the cavity model or with respect to the boundary conditions, the resonant modes of the structure are fixed. In the literature, whenever you are designing a wideband antenna, whenever you are designing a circular polarized antenna, whenever you are designing a defective ground plane structures antenna, there what happens, you do some modifications in the patch geometry. So when you do the modifications in the patch geometry, alterations between the interspacing between the various fundamental and higher order modes of the patch takes place, that realizes the respective response. It has been proved in the parametric study that the interspacings between these frequency changes and that leads to these characteristics. There is no addition or the subtraction of the mode is taking place. There is a interspacing changing between the mode is taking place. So from that perspective, it is very essential for us to understand the resonant modes, that is the fundamental and higher order modes, and we strictly call them as a driven modes. I will again stress upon what exactly a driven mode is and what exactly a eigen modes are. So let's begin our journey with respect to the understanding of the designs of microstrip antenna. We'll just brush up through the fundamentals and we'll go to the higher order mode discussion. Okay. Now in the flow, first I'll be talking about the fundamental and then basically the higher order modes of the regular shape MSA. Later part we'll do later. That is the broadband designs. Okay, this we have already done. In fact, this I was mentioning, M is equal to minus of n cross E. This is the fringing field model of the rectangular microstrip antenna, and on top of that we have represented the magnetic dipole concept. Remember, let it be any shape geometry. Let it be any shape geometry. One can come up across with these kind of magnetic dipole models that gives you the best picture of the radiating slots around the microstrip boundary. And once you get this picture, then the radiation pattern can be effectively evolved. As I have told you earlier, these two slots, they get cancelled out each other, and this is the one which is contributing to the radiation for the fundamental TM10 mode. There is very little bidirectional variation of the currents like which was there in case of equilateral triangular geometry. We have seen that. So because of that, the cross polar level, you can see that in case of ETMSA it was way up. In case of RMSA it has reduced. The main reason is there is very little bidirectionality. When I am mentioning very little bidirectionality, I already explained in the last lecture from where this bidirectionality comes, because of the source of TM02 mode. Now this we are going to understand today, why a given feed point location always excites fundamentals and higher order modes. Okay, remember they are all driven modes what we are talking about. I will just introduce what the difference between the driven mode and the eigen modes. Remember, this is a rectangular microstrip antenna. I have purposefully put the feed point. So when you put the feed point, the number of modes which are going to be excited are fixed. They are with respect to your feed point location, they are fixed with respect to the band you are working upon. If you do not apply a feed point location, then remember it is an open cavity. Open cavity, and you apply the boundary condition, you find out the resonant modes. So there all the modes of the cavity will come into picture, which will not get excited when the feed point is given. For example, when the feed point is over here, the driven mode will only show you TM10. Whereas when you do not have a feed point, eigen mode will show you TM10 as well as TM01 curve. which is not there over here. Why? Because it is a feed point location, and we have already seen it in earlier lectures. This feed point, when it is there along the center of the width, will not excite TM01 mode. Eigen mode will show you that, driven mode will not. That is the difference, and this driven mode approach we are going to consider, because whenever we design an antenna for any practical application, we always have feed point location fixed, and then only we design the antenna. So my stress will be on that rather than the eigen mode analysis. So this is already done. In fact, I have shown the voltage and current waveforms, as well as the field polarities are shown. This is the respective surface current distribution and the radiation pattern plot. Just to maintain the continuity with respect to the higher order mode discussion, I have just brought these few slides again rolling, so that the continuity with respect to higher order mode can be established. Okay, so this is roughly a TM10 mode. Radiation pattern is broadside and the cross polar level is this. Talking about the gain, okay, here purposefully I have given the gain values. Gain in case of microstrip antenna designed on a RT duroid substrate. RT duroid means dielectric constant is 2.33 and the tan delta is 0.002. So you can see a gain of the antenna to be 3 to 4 dBi at fundamental mode, whereas on air substrate one can go up to 8 dBi. Remember, this gain parameter is important. If you design the antenna on FR4 substrate, then the gain will be minus 2 dBi or minus 3 dBi. Why? Tan delta is more there. So gain is improved when you go to RT duroid substrate. Bandwidth is somewhere around 1 to 2% on a thinner substrate, and it goes to 4 to 5% on a thicker substrate. Thicker means 0.04 lambda, 0.03 lambda. But if you exceed this 0.04 lambda limit, bandwidth gets limited due to the probe inductance. So this is related to the bandwidth and the gain aspect, which you have not seen in the fundamental topic of rectangular, circular and equilateral triangular design. So these are some rough estimates with respect to the gain and the bandwidth which you will get across different substrate variation. Okay, it will not happen, definitely it will not happen 10 dBi gain you will obtain using a single patch, not possible. 6 to 8 dBi definitely it is possible, but why 6 to 8? Because depending upon what substrate combination, what is the thickness of the substrate, everything decides all these values. But getting a 10 to 12 dBi of gain from a single patch, it is not possible. Okay, fine. So this is related to the fundamental part of the TM10 mode, which we have already seen in detail in earlier lectures. Now just to have a continuation, these are the details related to the circular geometry. I'll just touch upon one particular point which we have not discussed in the topic when we discussed about the basic. We have said that one mode, which is a fundamental mode in circular patch, it will get excited when the feed point is over there. What will happen if the feed point is offset? What will happen if the feed point is offset? If you apply an offset feed point, that is neither along length, neither along width. Okay, if you just go back to the rectangular geometry, if I put a feed point over here, then what will happen? In addition to like if the feed point is over here, in addition to 10 mode, 01 mode will also get excited if I use a offset feed point location. Now in case of circular patch, let the feed point be here, since the resonant dimension, which is the resonant dimension, patch radius, is it changing across the different feed point location? No. In this direction also radius is R, in this direction also radius is R. So feed point, by changing the feed point location, the radius is not changing. So let it be offset feed point location, let it be a feed point location on X or Y axis. Resonant frequency in circular patch remains the same, and that is the beauty of the circular patch as against the rectangular geometry. That also can be one of the comparative analysis point with respect to RMSA CMSA. you get only one mode, whereas in rectangular patch you get both the modes. Okay, so that is the only point which I just missed with respect to our basic topic discussion. Rest of the points we already discussed. Just to continue on that point, polarization is linear. Now everyone knows what is radiation pattern. Radiation pattern we define in E and H plane, and the polarization is the direction of the tip of the electric field vector in space over a time. So polarization is linear in case of circular patch. It was so the same in case of rectangular geometry also, and thus you will see a high cross polar level. Sorry, low cross polar level. But I just want to put one more comparative analysis point here. In the previous lecture, for comparing RMSA, CMSA and ETMSA, we said RMSA has the lowest cross polar, whereas ETMSA has the highest. But look at the current distribution of CMSA. See, in case of CMSA also, the currents are moving like this. Okay? In case of RMSA, the currents were completely one directional in nature for the fundamental mode. Here, the currents are moving, so I can actually get components in the two directions. I can actually get the components in the two directions, although these components will cancel each other, okay, in the far field, but still some contribution will be there. And that's why CMSA has slightly higher cross polar level as compared to RMSA when you compare the radiation pattern. This point we have not discussed in the previous lecture when we compare RMSA, because we said RMSA has the lowest cross polar, ETMSA has the highest, but why? So, and CMSA lies in between. So this is the reason. Okay, so for any offset feed point location, your fundamental mode is only get excited, unlike the case in the rectangular patch, okay, where you get 1001. Our today's main topic thrust is on higher order modes, so with respect to that, I will try to align my discussion over here. Okay, so polarization is linear, radiation pattern is broadside, and compared to RMSA, it has a slightly higher cross polar level. But one of the big advantage of CMSA, talking about the higher order modes, it gives you a harmonic separation. So that is one of the beauty of CMSA, talking with respect to the higher order modes, no harmonic progression between the resonant structures resonant modes is present. Okay, so this is about this equation we have already done, and I have explained you the procedure to use this equation for designing a circular patch for the given fundamental mode frequency. Okay. Now this ETMSA we have just done in the last lecture, so I will not get into the details of that. We have already said that bidirectionally which is creates the nature of high cross polar radiation and lower gain in case of ETMSA against RMSA and CMSA. So I will not go into the more details of this. And of course, as I mentioned, L variation we do not consider for thinner substrates. Okay, so just to sum up, PM10 mode, which is a radiation pattern broadside of ETMSA, polarization is linear, harmonic rejection is better in circular patch, and in terms of, if I just put together gain, bandwidth as well as radiation pattern, definitely rectangular patch offers the optimum performance. We have said CMSA offers bandwidth maximum. How much? It was 182 and 175. So if I compare everything put together, because as an optimum solution, as a user if you want, I will say RMSA is better. In drawing also RMSA is better to be used rather than a circular patch. So likewise, from all this perspective, rectangular patch is the optimum solution against our other two regular shape geometries. Okay, fine. So now let's begin our journey with respect to the higher order mode excitation. As I said, this is very important topic with respect to the design of broadband, circular polarized or even deflected ground plane structure antennas. So I have shown the model over here. I have shown three feed point locations. Okay, feed point A, B and C. Now when the feed point is there at point A, that is along the length of the patch, 1-0 mode is bound to get excited. 0-1 mode will not come. if I put a feed point at point B, 0-1 mode will come, 1-0 mode will not come. But if I put a feed point at point C, 0-1, 1-0 both will come. How is their frequency spacing? As appearing from the structure, length of the RMSA is lesser as compared to width. 0-1 mode frequency will be lower. Why? Frequency is inversely proportional to your resonance frequency. What is the frequency equation? C upon 2L epsilon Re. Right? So, if length is more, frequency is less. So, likewise, if width is more, 0-1 mode frequency will be the first to appear, then 0-1, 1-0 will come. Okay? So, that's why I have shown the resonance curve. I have shown the resonance curve here for a feed point location C. I have shown the resonance curve here for a feed point location C. So, you will see 0-1 mode appearing first, then 1-0. Why? Width is more than length. Width is more than length, hence 0-1 mode is appearing first. Okay? Then comes another mode that is called as 1-1. This was not there when we talk about the previous two feed point locations. This is the next third order mode which is there. Okay? Then next mode which comes are 2-0 and 2-1. Now what are 2 zeros? What is 1-1? 1-1 means field or current shows one half wavelength variation along both the dimensions. 2-0 means field or current shows two half wavelength variation along the length of the patch, but the variation along width is not there. 2-1 means field is showing two half wavelength variation along the length of the patch, but only one variation along the width. Now, whether all these modes are there all the time, remember the mode will appear in the configuration when the impedance matching is there. Now, just imagine when the feed point was over here, was the impedance matching was taking place for 0-1? No. But if you put it over here, the impedance matching takes place. Same thing exists. In case of 2-0 mode, okay, I'll just explain with respect to 2-0. For 2-0, when the feed point is over here, how the field variation will look like is this. Two half wavelength variation. This is the feed point field variation for this. If I carefully select the feed point location where it coincides with the minimum field location of the 2-0 mode, it will get blocked. So, because along the length, it is showing two half wavelength variation. So, if I just draw RMSA, and then what is the feed point variation for this? This is the feed point variation for 2-0 mode if the feed point is over here. If the feed point is over here, then the feed variation will be like this, because the positive edge will go to that side. Right? So, here, if I put a feed point over here, you can just imagine if the feed point is put at L/4. If the feed point is put at L/4 from the center, then that mode is cut off. Why? Impedance is 0 over there. Impedance is 0 over there. Thus, by carefully selecting the feed point location, I can block. So, it is like a filter, remember. It is like a filter. By carefully adjusting the patch parameters or the feed point parameters, I can block some of the higher order modes or only allow certain higher order modes. This is what the beauty of feed point location driven modes is all about. Okay, now let's go to their representation. Then you will see how exactly these higher order modes look like. Okay, so this is the distribution of currents. Okay, this is the distribution of currents. 0-1, you can see variation along the width of the patch. Okay, one half wavelength. This is 1-0. Again, I am showing with respect to feed point C. This is 1-1. Okay, so you can see one half wavelength variation along a length, one half wavelength variation along the width. This is your 2-0. It is 1 half wavelength, 2 half wavelength along the length, and this is 2-1. So all these mode combinations will come into picture, and whenever you do any kind of modifications in the structure, the interspacing between these mode changes. Interspacing between these mode changes, and that yields a desired response. That yields a desired response. Now here, in case of this, if I would have put a feed point location over here, 2-0 mode could have get blocked. Why? Because in the center, 0 field line exists for 2-0 mode. Whereas over here and over here, field is maximum for 2-0 mode. Why? Because along the length now it is 2 half wavelength variation. Unlike the case of previous. You can actually draw yourself and then see on the piece of paper. There you will understand more. Okay, so these are all higher order modes. Remember, a general which is observation is whenever you have a unidirectional current variation, always the radiation pattern is broadside. Radiation pattern is broadside when you have a unidirectional variation. Whereas when you have two variations, 2 half wavelength variations, or I will say whenever you have odd integer multiple of half wavelength variation along the length of the patch, let it be 10, 30, 50, then you will get a broadside radiation pattern. So TM10 will give broadside radiation pattern, TM30 will give broadside radiation pattern. The nature of the pattern will slightly change, but it will be the same. Likewise, TM20 mode gives me end fire. Now what is end fire? The radiation pattern is like this. Broadside is this one, end fire is this one. Where it will be used, you just keep your antenna on your table. I want to receive the energy from anywhere else. In the planar area, not from the top. End fire radiation pattern is important. So I can operate that antenna at that particular frequency. So understanding of higher order modes of the patch is very important. Why? Because that gives me the assessment of which modes are present, and if I do any modifications in the patch geometry, which modes are bound to be coming into the lower frequency region, which will give me the desired responses. This is very important aspect from designing of wideband, dual band and circular polarized antennas. Okay. So here we have talked about higher order modes of RMSA. More and more you should, one important rule is the mode will be blocked if you are putting a feed point location at a null feed point of that. If you are not putting that, then that mode is bound to get excited. If I put a feed point location along W by 4 from the center, then TM02 mode also will get blocked. It will not get excited. Why? Because here the TM02 mode will have maximum current. So you put it here or you put it here, TM02 mode will not get excited. But other higher order modes will come. Okay? In fact, it is a very evolved, very detailed theory. And remember, these are all driven modes. They are not eigen modes. Why? Because we are putting feed point location. So, just to sum up, excitation of higher order modes is purely a function of feed point location. Radiation pattern gain, cross polar level, it is basically the function of surface current distribution on the patch. If a unidirectional current variation of 1/2 wavelength nature is there, broadside radiation pattern. Then if it is more than multiples of half wavelength variation, if it is an even multiple, end fire radiation pattern. If it is an odd multiple, it is a broadside. That understanding one needs to develop by looking at the current distribution. This is what I have mentioned. Odd half multiple, broadside pattern, cross polar definitely increases. Even always a conical maximum in the end fire direction. Increase in the modal order increases the bidirectional variation, and that changes the polarization because only one directional currents are not present on the patch. Okay. So, but remember, as I mentioned earlier also, there are advantages of high cross polar antenna also. It's not like that high cross polar antennas are not used. There are certain advantages of high cross polar antenna as well, especially from all personal mobile communication system where signal travel, signal incident, signal polarization is not guaranteed. Okay. So this is all about related to, in fact this generation of orthogonal currents on the patch leads to the circular polarized response. So this is all about higher order modes of the rectangular geometry. These are already in continuation with that. I have just given this slide. Here we already discussed this in the previous lecture, where TM02 mode always comes for TM10 mode excitation, and this is the main reason of cross polar generation at TM10 mode. At 10 mode, this is the main source of cross polar level generation. Okay, so here I have already drawn with respect to fundamental mode, the offset feed point will also locate that. The next higher order mode is TM20, and this is the KNM value, 3.05424. Now you just see, you can divide it 3.054 upon 1.84118. This ratio is not in harmonic value, which I mentioned earlier. This ratio is not in harmonic value, and that's why the circular patch gives a harmonic separation, unlike the rectangular geometry. So here, in case of circular microstrip antenna, it is the 2-1 mode, which is a higher order mode. You have a conical radiation pattern for 2-1 as well as 0-2. 0-2 mode is something very important. 0-2 mode means what? If I just draw the current distribution, the field distribution rather, the 0 means what? All along the perimeter, field is constant. So I will say all is positive. Whereas field is showing 2 half wavelength variation along the diameter. So the field will look like this. So you put a field point over here. This is the field distribution. And this mode is used in equal power distribution. In fact, when I am using a power divider, this is one of the mode they use for a circular geometry. Okay, one of the higher order mode of circular geometry. A TM31 mode, again 3 means 3 half wavelength variation along the length of the along the perimeter of the patch, and 1 half wavelength variation along the diameter. It gives me a broadside radiation pattern. In fact, few of the antennas, they do work on this mode. They bring that frequency to a lower frequency and tune it with respect to 1-1 mode frequency. Such configurations are there in the literature. So this is with respect to the higher order modes of circular geometry, and again in continuation to that, we have already seen the higher order modes of equilateral triangular geometry, that is TM11 and TM20. In fact, I just want to give one more beautiful theory related to this. In fact, I have mentioned over here tuning of fundamental and higher order modes of IT-MSA. Okay, isosceles triangular microstrip antenna. In that we have observed that how the patch will look like this. This is the isosceles triangular microstrip antenna, where these two side lengths are equal and this is different. So when I change this theta, okay, when I change this theta, spacing between 10 and 11 as well as 20, first 3 order modes facing changes, and that gives me a broadband response. Okay, so higher order modes, by changing one of the patch parameter, in fact a beautiful study is there in the literature. By changing this angle, one can change the current distribution directions and one can tune first 3 higher order modes. Of course, for tuning the last higher order mode you require a slot. But by integrating all these things together, we can actually have 3 modes coupled together and increase the bandwidth using a single patch. So in fact, when we go to the broadband microstrip antenna, resonant slot cut designs are there, and resonant slot cut designs you may not understand at this moment of time, but they are the most optimum configurations which we'll do later. So there, this concept of multiple tuning of modes using a slot or some modifications is being employed. So a single patch can give me a fantastic increment in the bandwidth. Okay, those things we'll do later when we actually go to the broadband microstrip antenna design. So next time now we will talk about the broadband microstrip antenna designs. Okay, then we'll do the techniques related to the broadband microstrip antenna. This is a small lecture which I conducted related to the higher order mode excitation. Remember, just to sum up few points, higher order mode excitation is a function of feed point location. Remember, it is a function of feed point location, and basic concepts only have to be applied for assessing the higher order modes, like whether 3-0 will come, 2-0 will come, likewise. You need to draw the geometry and then draw accordingly on the piece of paper the corresponding field distributions, and from that you can assess yourself whether that particular mode get excited or not. Again, they are all driven modes, they are not eigen modes. Eigen mode, everything is present. Driven mode, only the feed point specific modes will be present. And when you understand this, functioning of the antenna can be evolved very easily. And this is the case for all types of microstrip antenna design. So here we stop. In the next lecture, we will talk in detail about the broadband microstrip antenna using different techniques. Thank you.